Good morning, everyone. Today we're going to continue our discussion on multiple linear regression. So last time we looked at the model where we were regressing hourly wage, the dependent variable, on our explanatory variables. Our explanatory variables consist of education, experience, tenure, and number of dependents, all quantitative variables, and race, gender, and civil status, all categorical variables. Now, I just loaded the data. If we take a look at the wage, structure of wage, we could see that our race, gender, and civil status are character variables. They're categorical variables. There, character, character. Race is character, gender is character, civil status is character. So can we use categorical variables in multiple linear regression? Yes, we can. We can make use of categorical variables for multiple linear regression. Okay. However, next meeting, when we meet face to face, we're going to review this and say that if we're going to use matrix algebra in order to solve this, because we're going to do that, we're going to demonstrate how this is being computed because we're just using the LM function and it generates already the output. Okay, so this is, sorry. So this is our model, model 2. It's model 2 because I think we started with model 1 where we regress hourly wage on education, just a simple linear regression. But in this case, we're now using the whole, whole data set, and we're using the 7 predictors, 4 of which are quantitative and 3 of which are categorical. So if I run this, Control Enter, so you'll find here an object under our data, okay? An object called model 2. It's under data. So model 2 here, and it's a list consisting of 13 elements. Now, we said that if we're using all the predictors, we can just use this LM, hourly wage regressed on everything. The dot here indicates that you're regressing your dependent variable hourly wage on all your predictors, okay? And then to see what's inside our model, model 2, we use this summary model 2, and it will give us the result of our regression. This was what we did last time. And we said that let me redo this so that it will show us the summary model 2. Okay, we can see here that education is significant. At 3 stars means it's significant at 0.1%. Experience is not significant. It's significant, but at 10%. So if we're going to maintain the the standard of the level of significance alpha to be 0.05 or 5%, then we will have to reject the experience as a predictor of hourly wage. Tenure is significant. Race is not significant. And then gender male, gender is significant. Civil status and number of dependents are not significant. Now, we studied before what these 3 stars mean. These 3 stars mean that we are rejecting. So this is coming from a hypothesis here. The hypothesis here is that beta pertaining to education is equal to 0. Okay, that's the null hypothesis here. Education is equal to, the coefficient of education is equal to 0. And we, sorry, we reject this null hypothesis. We're saying that there's a strong statistical reason to believe that education, the value of the coefficient of education is not equal to 0. In fact, the average of that is 0.57. And we learned how to interpret this. We said that for every 1 year increase in education, Why year? Because the dimension of education is in years. For every 1 year increase in education, there's a corresponding, this one, beta 1 effect on hourly wage. Okay? Hourly wage, since it's in dollar terms, so there's a corresponding $0.57 or 57 cents US dollars increase in hourly wage. And then we indicated that there should be this qualifier, ceteris paribus, which means all things being equal, which means that if we're going to increase education by 1 year and hold the other constant, the others we're not going to increase, only education. We're going to increase it by 1 year, then there will be a corresponding $0.57 increase in hourly wage, again, ceteris paribus. So that's how you also interpret the others. Now, how about this? Race, white. Okay? If we take a look at our, okay, let me close this first. If we take a look at our data, let me view data as our wage here. So this is our wage. Okay, so what's happening here? How did these categorical variables become part of our regression model? Okay, so this is what happens. For example, race. For R, what happens is that R will take a look at the levels, at the different levels of race. And we know that there are two, non-white and white. Okay, so R will default into what appears first alphabetically. So even if white appears first chronologically, however, alphabetically non-white is first, right? So what will happen is that R will make this as the benchmark reference. We call it the benchmark. What happens when it's benchmarked? It is given a value equal to 0. Okay, and white will be given the value 1. So what happens is that this becomes 1, 1, 1, 1, and all the non-whites will become 0. All the non-whites. Same thing here. For gender, what will R do? So if you take a look at the levels, if there are 2, then you have female, just spell it out, female and male. And since female appears first alphabetically, this becomes the benchmark, and this is given the value of 0. Male will therefore get a value of 1. Okay. And lastly, you have civil status. Civil status also has 2. You have single and married and single. Now, since married appears first alphabetically, this becomes the benchmark 0, and single becomes 1. Okay, so in this case, for example, this will be replaced with 1, this will be replaced with 0, 1, 0, 0, 0, 1, 1, 1, 0, etc. So all the reference values will become 0, the non-reference one will become 1. Now what happens if it's if it's okay, by the way, now what happens is that when you have a categorical variable that's used for regression model, you introduce what we call a dummy variable. Dummy. Why is it called a dummy? Because you give it values of 0 and 1. That's why it's called dummy variable. So how many dummy variables are we going to introduce for race? The answer is always equal to k minus 1. So what do you mean by k? K refers to the levels. So for race, there are 2 levels, non-white and white. So how many dummy variables will be introduced? 2 levels minus 1, therefore only 1 dummy variable. So for race, ito lang yung dummy variable, only this one. Okay, there will be no other dummy variables for race. And what will be the dummy variable look like? It will look like this will be 1, okay? This will be 1. So I mentioned here 1, 1, 1, and all the non-whites will be 0. Okay. Now what happens? Hello? Am I still connected, class?
Yes, sir.
Okay. All right. Now what happens in the case where you have more than two levels? For example, one of your variable is year level. So let's suppose we were we were doing some research and we were gathering data on students of different universities. So you have frosh, okay, sophomore, okay, junior, senior, and maybe let's put another category, graduating. Okay. So if we were putting this in R, okay, what will now happen? Again, this will be converted into dummy variables. Okay, dummy variables. So how will this be? Okay, since frosh will appear first alphabetically, then this will be given a zero value. This will be your benchmark. And the others will be given 1, 1, 1, 1. So even the graduating student will be given 1. Why is this so, class? Because again, it will generate dummy variables. And how many dummy variables will be generated? It will be k minus 1. Why k minus 1? Okay, so how many dummy variables for year level? Since there are 1, 2, 3, 4, 5 levels, say we have 5 levels, and then minus 1, so you'll have 4 dummy variables. Now, how will the dummy variables be introduced? So since frosh will be 0, so let's suppose this is our year level. So you have here, let's say, senior, sophomore, example only, graduating, frosh, junior, junior, frosh, and then sophomore. So for example, this is our data. I'm sorry, it's not aligned. No? But let's suppose this is our data. And we said this will be converted into 4 dummy variables. So what will it be? You'll have, for example, year level, sophomore, year level, junior, year level, senior, and year level graduating. So 4 variables will be introduced. 1, 2, 3, including graduating. 4. So how will this go? Sophomore, this is sophomore. It will be 1 here. Junior will be 0, 0, 0. Okay, so for this observation, which is sophomore will be 1, junior will be 0, senior will be 0, graduating will be 0. Okay, suppose this is senior. So this will be 0, 0, 1, 0. Graduating 0, 0, 0, 1. Okay, and then frosh. What will be frosh? 0, 0, 0, 0. Okay, so may I have a show of hands, please? Are all the levels accommodated? Are all the levels now present here? If we're introducing 4 dummy variables, are all the levels taken into consideration? May I see your chat if it's yes or no, please? I'd like to see your chat, please, if all the levels, frosh, sophomore, junior, senior, and graduating are accounted for. Answer, please. Yes or no? Okay, Jared, thank you. Kindly share your answer to everyone, Jared. Okay, Miko, thank you. Colin, thank you. Okay, all right, and that's good. Yes, you're correct. All the levels are accommodated. How come? Okay, so this will be replaced. This variable, this categorical variable, the year level will be replaced by 4 dummy variables. consisting of year level sophomore, year level junior, year level senior, graduating. And why not introduce also another dummy variable for frosh? Okay. Why not introduce? We can have here another variable for frosh, and this will be 1, right? Now, it's not done because, okay, what will happen is that there will be perfect multicollinearity. Okay, please take note of that. Perfect multicollinearity. Perfect multicollinearity. So that will happen if the number of the dummy variables that you introduce is the same as the number of levels of the variable. Perfect multicollinearity. Okay, and that's what we also call the dummy variable trap. It will yield uh, it will yield a wrong solution. Okay, unless and since this is happening behind the scenes, now the software already knows what to do. So it will not introduce 5 dummy variables, but only 4. Okay. Now, a question could be, what if I don't want the frosh to be my benchmark? Because this is out of convenience. This is just by convention. This is just by alphabetical arrangement. What if I want the benchmark to be the graduate? Can that be done? Yes. Okay. But I'll illustrate that on Monday, and it will take some re-leveling. It will be better for us to discuss that when we're face to face, but it can be done. Okay, so going back now to our model. Okay, going back now to what happened here. Okay, so now you can see that you have here race and then white. Why? Notice the non-white is not here because it is the benchmark. And how will you now interpret this? So dummy variables will now be interpreted in the light of, with reference to your benchmark. Okay, race white. Okay, so what does this mean? Assuming that this it's not significant, so the null hypothesis is that beta 1, 2, 3, 4, beta 4 is equal to 0. Okay, and the p-value is 0.8. So we fail to reject the null hypothesis that the coefficient for race is not equal to 0. We fail to reject that. So there's strong reason to believe that there's no effect, there's no distinction between being white and being non-white. That's the meaning of this. Because we're saying that beta is equal to 0, so it means that there's no difference between, there's no impact on the hourly wage if you're white or if you're non-white. Okay, but assuming this is significant, let's assume that this p-value is significant, less than 0.05, then how do we now interpret this? It is now interpreted like this. On the average, white people earn, okay, 0.11 centavos or 0.10996 centavos or dollars more. Okay, but why more? Because this is positive. So you're now benchmarking this value here to the benchmark, which is non-white. Okay, didn't I tell you that non-white is the reference? It is the benchmark. So you should interpret this as the white employees on the average tend to have around $0.11 more than their non-white counterparts, ceteris paribus. Okay, so I hope that's clear, class. No? Same thing here. Here, gender male, and it's significant. Okay, so the null hypothesis here, which is beta 5, why 5? Because 1, 2, 3, 4, 5. In our list, it's the 5th regressor. So beta 5 is equal to 0. That's our null hypothesis, right? And what's our conclusion? Since the p-value is significant at 0.1%, highly significant, then we fail to reject the null hypothesis that gender male is 0. Okay, how to interpret this? On the average, male employees receive $1.76 more than their female counterparts. Okay, hourly wage they receive $1.76 in terms of hourly wage more than their female counterparts, ceteris paribus. So this is statistically significant. This, on the other hand, is not significant. Okay, civil status. Therefore, we can see no distinction between the effect of your civil status on hourly wage. Number of dependents also is not significant. Okay, let me pause for a while and entertain questions. If you have any questions, if you have any clarifications, please feel free to ask it now. Or I'll ask it in the affirmative. Is the discussion clear so far, class? Please requesting for your feedback if so far okay yung ano natin. Okay, good. Thank you. All right. Thank you. Okay, now on Monday, we'll be taking a look at this. No? We'll be learning how to compute for this because it's important also for us to know what's happening here. How did R generate this solution? It made use of a combination of statistics, made use a combination of calculus, differential calculus, and also linear algebra. On Monday, we will just take a look at the linear algebra side. And we're going to learn how are these computed. Okay? And then over here, class, you have here the standard error, which is similar to the standard deviation of your residuals. Okay? Okay, before I go there, by the way, now, if you take a look at Model 2, if you run Model 2 names, okay, Model 2 names, it will give you what's inside Model 2. So what's inside Model 2 are objects here. So we have here the coefficients, the rank, residuals, okay, the fitted values. So for example, if I print mod, okay, head, sorry, let's just take a look at the first 6. No, mod 2, not here. So mod 2, how do I access this object inside mod 2? How do I access them? We type $, right? Okay, $, again, mod 2, then dollar, shift. Okay, then you have here, for example, coefficients. Control Enter. It will now give us the values of your coefficients, the one that you saw here in the model. Intercept is -3, okay, -3.38 something, okay. So these are what we got a while ago. Okay, I think I forgot to ask one question. What number is that? Here. So let me rerun this, class. What's the meaning of, what is the meaning of, okay, summary. What's the meaning of this intercept, class? Regardless of whether it's significant or not. In this case, it's significant. What's the meaning of this? The general rule is that the intercept is the value of your response variable, of your dependent variable, when all your predictors are all equal to 0. So can anyone, please? Okay. This negative, although it has no physical significance, no? Because you cannot have an hourly wage equal to -3.4. Let me just round it to -3.4. How can an hourly wage be negative? Does it mean that you're the one paying the employer or the company? Okay, so it's absurd. But nevertheless, we still include this in writing our model. So what's the meaning of this? So it's the hourly wage -3.4 of a person who has, okay, who has what? Who has 0 years of education. So he has no education, 0 years of experience. Okay. 0 years of tenure, 0 years of zero number of dependents. Okay, and and please continue, class. And what? Who is, let me repeat, negative 3.4 is the average hourly wage of a person who has no education, no experience, no tenure, and class. Anyone, please? We still have three variables here. And class, who is male? Okay, thank you, Colin. Kaso opposite, opposite. Yeah, I think you guessed it right, but on the other side, no? So, yeah, thank you, Colin. It's female. Bakit female, class? Di ba we made this into a dummy variable? Sino yung zero dito? Si female appears first alphabetically. So we gave it the zero value, right? So, sabi natin, yung intercept is the value, average value, independent variable value, yung hourly wage of a respondent who has zero in all of this. So, zero education, zero experience, zero tenure. Ano yung zero pag race? Female, di ba? Non-white pala, sorry. Non-white, who is female, and who is married. Okay. Kasi yung married dito, zero yan. Dito yung female, zero. Yung non-white, zero. So let me repeat that. The average hourly wage of a person who has 0 years of education, 0 years of experience, 0 years of tenure, who is female, who is non-white, who is female, and who is married, and who has zero number of dependents. Okay, so that's the average hourly wage of this person who are all zeros here. Okay, which we said that, okay, we don't put too much practical significance on that because it's impossible naman for that person to get a negative 3.4. Siya pa yung magsasweldo sa company, di ba? That's not possible. However, class, when we're writing this model, we include the intercept, okay, regardless of whether it's significant or not. Okay, so our model here will be hourly wage. Okay, let me just recite that because I don't have my digital pen with me. Hourly wage is equal to negative 3 point, let me just round it off, negative 3.4 plus 0.57 times education, okay, plus 1.14 times tenure, plus 1.76 times gender, plus a certain error term, plus epsilon sub I sa dulo. No? So those four parameters that I included, intercept, and then education, and then tenure, and then gender. So those four. We're not including experience because it's not significant at 5%. Okay, so let me pause for a while and I would like to confirm from you if so far we're clear on the interpretation of this. I hope you'll respond, class, because I want to know if I'm getting through, okay, or if you want to repeat a particular portion in what I've discussed. Okay, honor me please with your feedback. I'll really appreciate that. Okay, good. Okay, looks like no questions. All right, so let's continue. So is that the final model, the model that I just recited a while ago, consisting of beta times education, beta times tenure, beta times gender, plus the intercept? Notice, class, that when I write the equation, I don't write gender male. I just write gender, okay, plus gender times beta. Why? Because gender, class, is the variable. Okay, so what happened here was that R just made some adjustments here so that we know what is the non-reference variable. The one that's reflected here is your non-reference. So therefore, the one that's not reflected here will be your reference. Okay, by the way, if year level was part here, if you recall a while ago, then we would have here year level sophomore, year level junior, year level senior, year level graduating. There will be 4 dummy variables, as we know. Because there are 5 levels, therefore 4 dummy variables will be introduced. Okay? All right. Okay, then we're going to discuss this in greater detail next time. This one, let me just discuss this while we're here. Okay, you have here your F statistics, 43.54, and then we have your degree of freedom 1 and degree of freedom 2, and then your p-value. So what's this? What in the world is this? So this is called your analysis of variance test, or it can be called as the goodness of fit test, or joint test. Okay, why? Because the null hypothesis here, may null hypothesis din to, ah. The null hypothesis is that the reason why it's called joint is because you're testing beta 1 is equal to beta 2 is equal to beta 3 is equal to until is equal to beta dot 7, because there are 7 predictors, okay, excluding intercept, and it's equal to 0. Okay, so this is the joint test, or this is the goodness of fit test, or the analysis of variance. Okay, so what's our conclusion here? The p-value is less than 0.05. Therefore, we reject the null hypothesis that all of our parameters are all equal to 0. We have strong statistical reason to believe that at least one of these is not equal to 0. And we know that, okay, gender is significant, tenure is significant, etc. Now, this one, okay, 2.95, we're going to learn how to compute this. It's a reflection of the of the standard deviation of your residuals. Okay, the higher the standard deviation, the more let's say the more uh, what's the good word for that? Not unreliable will be the model. Okay, we would want a model that has a low residual standard error. Okay, and then this one, 500 degrees of freedom for your ANOVA, which is specified here. Here you have 7 and 518. So there are 2 degrees of freedom. The first degree of freedom, the F1, is your number of predictors. So how many predictors do we have excluding your intercept? Education, experience, tenure, race, gender, civil status, number of dependents. So there are 6. Okay, 7. 7 predictors. So that's your degree of freedom 1 here. Degree of freedom 2 will be your DF2 follows the formula K N minus K minus 1. Okay, N is the number of real respondents, the size of our data, which is 526. And then minus K, what's K? K is the number of predictors, which is this one. Okay, minus 7, and then minus 1. Why minus 1? Because we lose a degree of freedom when we compute also for the intercept. Okay, N minus K minus 1. Okay, so the number of respondents minus the number of predictors minus the intercept. So that's why you have 518 degrees of freedom. And this is where you got this degree of freedom. Okay. All right. And then lastly, you have your adjusted R squared. Okay. We'll discuss what multiple R squared means and adjusted R squared. And you notice that it's 36.19%. What's the meaning of this? It means that the variability, the variance of hourly wage, which is our response variable, our dependent variable, okay, 36.2%, 0.19% of the variance of the variability of hourly wage can be explained by our model, by this model. We can explain 36.2% of the variability of hourly wage. So what happened to the other one, the 63.8? Okay, this is now your unexplained variance. Okay, that is what something the model cannot explain. So what does this entail? Maybe there are other uh, variables out there that should have been included, because what the model can only explain is 36.2%. Okay, once again, I'd like to stop for a while and ask for your feedback if we're clear so far. Okay, all right, thank you. So I'm waiting for the others to respond. Thumbs up, please, if we're clear. Okay, thank you. Okay, so let me now go to back to our lesson. So the question is that the final model? We have rejected 1, 2, 3, 4. Okay, the answer is no. Okay, because we're going to use what we call stepwise regression. Stepwise regression is a process where we only uh, remove one variable at a time. Okay, so last time we said that in order to move from one model to another, we have to look at the t-value or the p-value. If we take a look at the t-value, we will have to choose that which is the lowest t-value in absolute terms. Okay, definitely, you notice that the significant variables, they will always have higher t's compared to the insignificant. Okay, they will be always significant. And the one even with the highest t will usually be the most significant, in this case, education. So that leaves us with the others. And the lowest absolute value of t is this one, 0.257. The absolute value. Okay, you don't look at the negative numbers. You just take a look at the number itself. Okay, so what will happen now? We will treat race as our living variable. Okay, we will have to remove race from our model, okay, because it's the one that least contributes to explaining our variable. Okay, now what's the importance of doing stepwise regression? Doing stepwise regression may come up with a solution where if we remove them, the insignificant variables one by one, okay, later on in the process, another variable which used to be insignificant might become significant. Okay, so that's the case. So now we have only 3 variables that are significant. Let's see what happens as we do stepwise regression. Okay, so what we did last time was we came up with model number 3, where the living variable is equal to race. How did we choose race? Race is the one with the lowest absolute t-value. Okay? Or corollarily, it will be the one usually that will have the highest p-value, the least significant. Okay, so we're now creating another model, model number 3. Same thing, hourly wage regress on 1, 2, 3, 4, 5, 6. So the 7 variables became 6 now because we are removing race. Okay, same thing, data is equal to wage. All right? Okay, so what's this? This is no longer needed. Okay, I'm going to run model number 3 and then summarize it. Okay, now what happened? Okay, you still have 3 significant predictors. Experience is still significant, but at 10%. Okay, so what do we have here? So education, tenure, and gender still remain significant. Experience is significant only at 10%, while civil status and number of dependents seem to not have any effect on hourly wage. Okay, but so our goodness of fit test class. Okay, our beta 1 is equal to beta 2 is equal to dot 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 beta. So there will be no more beta for the race. Okay, and they're all equal to 0, and we reject that null hypothesis. Okay, now what's the difference between this model, model 1, and model 2? Now notice that we removed race, right? And despite the fact that we removed race, what happened? Our adjusted R squared here, model number 2, is 36.19. On the other hand, our adjusted R squared here, 36.31. Okay? So we're able to explain more our dependent variable if we remove hourly wage. Okay. So what's the basis now of choosing between model 2 and model 3? Okay, because we have to have a basis for that. Okay, and if you can see here, there are now only 500, there are 519 degrees of freedom, okay, higher degrees of freedom, because the degree of freedom 1 is just 6. Degree of freedom 2, which is n minus k minus 1, so that's 526 minus 6 minus 1, that will now be 519. And what's the p-value? It's much less than 0.05. Therefore, again, we fail to reject the null hypothesis that all the betas are all equal to 0. Okay. Now, which is better, model 2 or model number 3? Is there a statistical test for that? Yes. Okay. There's a statistical test for that. So let's take a look at this quickly. Okay. Model number 2 has how many predictors? Model number 2 has 7 predictors. Model number 3 has 6 predictors. Okay. All right. Since now there's a name for this for model number 2. It's called your unrestricted model. Unrestricted because you are comparing it with model number 6, which is your restricted. Okay, unrestricted versus restricted. Now, what we're testing here is that, so what's the difference between model 2 and model 3? The difference is in the race variable, right? So we are testing if indeed race is equal to 0. So that's our beta number, I think that's beta number 4. So beta race is equal to 0. That's what we're testing. Okay? That is what we're testing, beta of race is equal to 0. Because if our analysis of variance says that we fail to reject this, then it means that if we fail to reject this test, it means that race is equal to 0. Now, if race is equal to 0, which model is better? Kindly chat, please. I hope you got my question. I'll repeat my question, okay? I'll repeat my question. You have two models here. Model number 2 has 7 predictors. Model number 3 has only 6. What's the difference between them? It's the race, because we removed race from model number 3. So what are we testing? We're testing if is beta for the race equal to 0. Because if it's equal to 0 statistically, then we follow model 3, right? Because there's no need putting race if it's equal to 0. But if it's not statistically equal to 0, then model 2 will prevail. Okay? Yeah, thank you, Jenica, restricted. Okay. So model number 2 is your unrestricted, model number 3 is restricted. Okay, so the function for that is this one, ANOVA, analysis of variance. model 3, which is your restricted, and model 2, which is your unrestricted. Okay, let's run that, please. Okay, let's run this class. ANOVA, model 3, model 2. Okay, what appears, class? Okay, let's run this. Control Enter. Okay. So take a look at this model number 1 here is, this is the complete model. This is the unrestricted model because, sorry, this is the restricted model. It doesn't have the race here. Model number 2 is the unrestricted. Okay. So what are we testing here? We're actually testing that. Okay, let me go to the uh, not logic, to the fundamentals of this. We said that the difference between model number 2 and model number 3 is that there is no model number, there's no race variable in model number 2. So we're testing if beta for the race is equal to 0. Okay. In what model is beta race is equal to 0? It's in model number 3, right? Because we removed it. So in effect, we're saying what we're testing is if this beta race is equal to 0. And what's our statistical conclusion? The p-value is 0.97971 or 0.8 practically. Okay, and it's much greater than 0.05. Okay, 0.7971 is much greater than 0.05. Therefore, we what do? We fail to reject what? What are we failing to reject? The null hypothesis that beta race is equal to 0. Right? Indeed, beta race is equal to 0. So if that's the case, if beta race is equal to 0, there's no sense in using model number 2 because model number 2 has race with it. Okay? So that means that model number 3 is the preferred model. All right? So just take note what's being tested here. The difference in the parameters. Sometimes you may have two parameters that's being reduced, deleted. Okay, pause for a while, class. Is our discussion clear so far? Okay, please remember the test there. Restricted versus unrestricted. And others would say that the null hypothesis is the restricted model is better. Because in restricted model, it's the one that has beta race is equal to 0. Okay, so, okay, thank you. Okay, now let me go here. So if we take a look at this one, class, what will be, could you kindly, and then my question, okay? So let me entertain some questions. Yes,
Sir, it was me. Sorry, can I ask lang ulit?
yeah,
What was
sure,
the
sure.
grounds? What was the grounds for making model 2 better again?
Model number 2, what's the ground?
Yes, sir. Why is it better than
Yeah,
model
model
3?
number 2, model number 2 includes race, di ba? Model number 3 does not include race. So the question is, which is better, include race in your model or do not include race in the model, right? So it's tantamount to saying, itong race na to, no? Is this equal to 0? Because if this is equal to 0, why will you still put that as a an independent variable, right? So we're testing here, technically, statistically, what we're testing is that beta pertaining to the race is equal to 0. Okay, aka another way of saying that is when is race equal to 0? If it's restricted, no? Okay, so another way to put the statistical test is that the restricted model, the one where race is deleted, is not included, is the better model. Okay, so it's another way to put it. But actually, the test there is beta of the race is equal to 0. Okay, so what happened? Let me repeat this process. What happened when we run the ANOVA here? When we run the ANOVA, the p-value is 0.79 or practically 0.8. So what's our conclusion there? Remember, when the p is low, the null must go. So if the p is not low, then we cannot let go of the null hypothesis. What's the null hypothesis? Race is equal to 0. Okay, or restricted model is better. So what's our inference? Since we cannot reject that hypothesis, then we're saying that we fail to reject the null hypothesis that beta race is equal to 0. We cannot reject that. Indeed, statistically, beta race is equal to 0. Therefore, if beta race is equal to 0, the restricted model, the one without race, prevails. Okay? Eliza, was it Eliza? Eliza, did that address your question?
Yes, sir. Thank you.
Okay. Thank you. Okay, keep your questions coming, class. Appreciate it, Eliza. Thank you. Okay. All right. So again, we go to stepwise regression again. What will now be the living variable? The living variable, as we said, you take a look at it either at the t value or at the p value. It's easier to take a look at it at the t value. So we only have 3 candidates actually, the ones with no asterisks. Okay, excluding intercept. Okay, even if intercept is not significant, you will not choose intercept as part of the leaving variable. So the answer is, class, number of dependents, right? Number of dependents. Okay, so this will be our leaving variable. So number of dependents will now be deleted, will now be removed. So if you take a look at model number 4 now, model number 4. Okay, this is model number, I'm sorry, I got disoriented with the, so summary, model number 3. So this should be model number 4. Oops. Where's model number 4? Okay, here. Model number 4, okay? Hourly wage regression, education, experience, tenure, no more race, gender, civil status, no more number of dependents. 1, 2, 3, 4, 5. Originally 7 minus 2, minus 2, so there are now only 5. So let's run this, model 4. And let's get the summary. Okay, so experience became worse, no? Okay, kanina medyo may 1 star, 1 dot siya. Ito, si civil status siya yung naging siya naging mas significant, no? Although hindi pa rin siya significant. Okay, but same plus same 36.21. So if we compare it with the previous one, so the previous one had 36.31. The next one had 36.21. But good thing this is not the the be all and the end all basis of choosing which is the better model. But suffice it to say, class, that model number 3 has a higher adjusted R squared compared to model number 4. Okay. Overall goodness of fit test, it's still significant. Okay. So how do we now, class? How do we now determine which is better? Is it model number 4 or model number 3? So this is the test. Okay, model number 3, okay, has number of dependents. Model number 4 does not have number of dependents, which tells us, class, that the null hypothesis here is that beta, that's beta 7 actually, is, or which is the number of dependents, numDep is equal to 0. So that's what we're testing. Beta 7, or the number of dependents, is equal to 0. Okay? So if we are able to show that statistically, this is, we cannot, if we fail to reject this, then we are saying that statistically this is equal to 0. If this is equal to 0, then the restricted model is better, because the restricted model did not include number of dependents. The unrestricted, which is model number 3, in this case, still includes number of dependents. Okay, so if I run this, and we have a, okay, take a look. P-value is 0.184, which is higher than 0.05. Therefore, we fail to reject again the null hypothesis. What's a null hypothesis? That beta 7 is number of dependents. There's strong reason to believe that this is statistically equivalent to 0. Okay, therefore, the better model is model number 4, this one, the restricted model, because it did not include number of dependents. Okay, all right, let me pause for a while. Okay, and please chat, please, if all is okay, if you're able to follow along, if you understand. Okay, thank you. All right. Okay, good. But I wish to have more responses. There are only 9 that responded. That's not even, that's only 25%. I just want to know that you're there and that you're able to follow along. Okay, good. Thank you so much. Okay, thank you. Thank you. I appreciate that. Okay, so we're now going back to model number 4. There are only 2 insignificant variables left. It's either experience or civil status. Okay, and then from the t-value, you can see that experience is 1.58. And then civil status is absolute value 1.95. So experience has the lower t-value. So this will be your living variable. So take note, even if civil status is algebraically the lower number because it's negative, still we take a look only at the absolute value. Therefore, what will be living, yung aalisin natin, is experience. Okay? So we now go to model number 5, this one. So model number 5, education, tenure, gender, civil status. Okay? Correct, class? Education, tenure, we removed experience. Okay? So far, we have removed 3 variables, right? Race first, and the number of dependents, and then experience. So 4 are left. Okay, so let's run this, model number 5. And let's summarize this. Okay, now let's see. Now take a look now at our final model. Education, tenure, gender, and civil status are all now significant. Even civil status has become significant. Okay, at yeah, 1 star, that's at 5%. Okay, now let's go back to model number 1. Had we, at the onset, model number 1, where are you? At the onset, sorry about the scrolling. Where's my model number 1? Okay, this one. I'll just summarize this. Oops, sorry. Let me run model number 1 again. Okay, I just want to illustrate this. Just model 1. Okay, LM. So we have hourly wage, regressed on everything, data is equal to wage. Okay, model number 1, control enter. Summary natin. Summary, mod 1. Okay, take a look at this class. Okay, sorry, let me just run it here. Am I right? Yeah, there, class. So this is model number 1. Had we stopped here, what would have happened? We would have only education, tenure, and gender. Okay? Civil status would not have been significant. Number dependent, it's okay because in the final model, this was also not significant. Experience is also not significant, and race is not significant. Okay, there was only one, let's say, discrepancy because our final model shows that civil status is significant, while here it's not significant. Okay, so what am I trying to impress here? I'm trying to say, class, that okay, that stepwise regression is important, although it has its weaknesses. However, when you run a multiple regression model, you do not automatically cross out all the other variables that are not significant. Okay, as shown in our case now, there was one variable that later on became significant, and that was civil status. Okay, any questions, class?
Third question.
Yes, sure, sure. Sino to?
Sir,
Jared?
paano po pag,
Oh,
Jared
Jared.
po. Sir,
Yeah,
paano
okay.
po pag sobrang daming variables? Isa-isa pa rin po namin itetest para po magawa yung stepwise na regression.
Oo, oo. But there's a function OLSRR which we're going to use maybe sa Monday. No? Itong OLSRR, you can use its function so that automatic na siya na magproproduce itong lahat na to. Okay? The reason why we're going through this is that I want you to understand the process. Okay? Imagine if there were 20 independent variables. And then you'll have to do stepwise for all of them. That can be time consuming, right? What we want is to have understood the process first, and then we go to the automatic way to do it. So there's no point in going through this one by one, step by step. Okay, the only purpose that we did this is for you to understand what was the process, what was happening, how was the deletion of the variable being done. Okay, there are actually two ways of stepwise regression. One is forward stepwise, and the other one is backward stepwise. What we did just now is a backward stepwise regression because in a backward stepwise regression, we throw in all the variables first, all the independent variables are included, and then remove them one at a time. Okay, with the process that we with what we just did. On the other hand, for the forward, iba. You start with nothing, and then you insert the variables one at a time. Okay, so sometimes you arrive at the same result, sometimes not. So which makes this model, this type of method, uh, quite weak in the sense that technically dapat if you're using forward or you're using backward, then you should come up arrive at the same answer. But sometimes you do not. So that's a inherent weakness of this method. Okay, but it's also wrong just to take just to remove all the other variables. Okay, mali din yun. So you will have to we will have to do stepwise also uh, to a certain degree. Okay, did that answer your question, Jared?
Yes, sir.
Okay,
Thank you.
good. Thank you. All right. So so our final model, but we have to test first, okay? Whether, remember that for model number 5, what we removed was, what was that variable class? What was the living variable for model number 5? Anyone? It was, hello class. What was the living variable for model number 5? Okay, it was not number of depend, it was experience. Okay, thank you. Okay, experience. So we're testing experience is, I think, beta 2, right? Beta 2, which is experience, is equal to 0. We would like to test this. Okay, so is beta 2 really 0? Because if we fail to reject this, then we may conclude that indeed there's strong reason to believe that this is 0. And if this is 0, then it's like saying that, yeah, model number 5 is better. The restricted model is better. Removing experience will not really improve the model. Okay? All right. So if I run this, delete again, and test whether our model is okay or which model is better, there. Okay. Again, class 0.11, 0.12. So the hypothesis that beta 2, which is the experience, is equal to 0, is we fail to reject that. Okay? We fail to reject that beta 2, which is experience, is equal to 0. So there's strong statistical reason to believe that it's possible for experience to be 0. Therefore, we do not include that in the model. Therefore, model number 5 prevails. Okay, ito yung model number 5, hourly wage, education, tenure, gender, and civil status. Okay, so far, are we clear, class? Are we clear so far? All right. So, paki-chat please kung clear tayo so far. Okay, good. Thank you. Okay, thank you. Thank you. All right. So let's go now. So we know the final model, class. No? In the interest of time, I have only around 6 or 7 minutes. I'll just first, okay. So on Tuesday next week, on Monday next week, what we're going to do is we're going to uh, discuss how was the how were the values of the coefficients, standard errors, the t-value, the p-value, how are they computed? Okay, kasi parang we're like operating in a black box. We just put in the dependent variables, the independent variables. Okay. By the way, before I'm sorry, I forgot. Before I leave this, okay, let's write the final model here. So what's our final model? Let's take a look at model number 5. Where's our model number 5? Summary. Okay. Summary model number 5. Summary model number 5 is, okay, hourly wage. Okay, hourly wage. Sorry for the writing. Hat, okay, I put a hat there, is equal to hourly wage sub I, okay, is equal to negative 2.16. I'll just drop the other decimal places, and then plus 0.53, rounding off to the 2 decimal places, times education, educ sub I, plus 0.15 times tenure, tenure sub I, and then plus This is 1.71 times gender plus negative 0.68 civ status. Okay, will I put an epsilon here, class? Plus epsilon ba to? E sub I or not? Do I put here epsilon sub I or not? What's your answer, class? Answer is yes. Thank you, Isabel. Please share your answer with everybody. How about the others, class? What's the answer? Should I put epsilon here? Answer is no. Okay, no. That's correct, class. No. Why? Because we're computing for the predicted value. Yan. Okay? This is your predicted value. Okay, so there should be no E plus epsilon sub I here. However, if I'm modeling hourly wage, okay, our actual hourly wage is equal to, all right. So you have this, class. This is our model. This is the predicted. So is hourly wage equal to the predicted, class? Are they always equal? Okay. So I'm copying this one. I'll just represent it by this one, hourly wage. Predicted. Are they equal, class? Okay, no, they're not. Okay. And what's the difference between them? The residual. So we put here epsilon sub I. Okay, that's when we put our epsilon sub I. If we're coming up with an equation with the actual value of your dependent variable. But if you're doing the predicted value itself, then this is already the predicted value. So no epsilon sub I here. Okay, good. Okay, so I don't think I have, I was thinking of at least introducing this. Nevertheless, I'll just show you this equation, class. Okay, so as we end, next meeting, take a look at this. Where's my equation? Oh, it's not here. Okay, great. Okay, I'm sorry, it's not in this file, okay? But next meeting, we're going to show class that, let me end in this equation. How do you compute for the beta? The betas, class? The coefficients. So it can be shown, class, that the coefficients, and I end here, is equal to x inverse times x, x transpose times x inverse times x transpose times y. Okay, so we're going to look at this equation next meeting. Okay, this very, very famous equation in linear algebra. X refers to your matrix of your independent variable. So andito kasi education, experience, tenure, gender, race, civil status, and number of dependents. So di ba may mga values tayo nila, no? Andyan yung matrix na to, which is your wage data, wala lang yung hourly wage. And then next meeting, I'm going to show you that we have to have a column also for your intercept, for your beta null. And then we're going to generate here a columns of 1 plus mga values na to. That will now be your matrix X. So how do you compute for your coefficients? Perform this in matrix algebra. X transpose multiplied by X and then get the inverse times X transpose times the Y matrix is the hourly wage. So ito yung mga values ng hourly wage. We're going to call that Y. And this is your X matrix. Okay? And we're going to show you that indeed, if we perform this, okay, we can get the answer that was given to us. All right. So let me now